Welcome to the Verisense course series, where we will explore the Verisense network, a groundbreaking blockchain infrastructure designed for the era of decentralized intelligence. This series offers a comprehensive analysis of the Verisense network, from its foundational paradigm shift and core technologies to its architecture and vast application potential. Our goal is to empower you to master Verisense and build the next generation of decentralized applications. In this course series, we will systematically explore all the key aspects of Verisense. Today, in our first lecture, we will concentrate on the fundamental concepts and value proposition of Verisense. In future sessions, we will dive into its technical implementation, covering the innovative monitoring consensus protocol, the nucleus environment designed for secure on-chain agent operations, and SenseSpace, which serves as a powerful and universal space for multi-agent orchestration. The main learning objectives for this lesson include analyzing the passive dilemma of traditional blockchains. We will explore why the inherent passivity of current mainstream blockchain architectures poses a fundamental constraint, especially in the face of the decentralized artificial intelligence (dAGI) movement. Understanding the core concept of the active blockchain, we will define the active blockchain concept as proposed by Verisense and elucidate how it provides on-chain programs with unprecedented autonomous interaction capabilities, clarifying Verisense's value proposition and core contributions. We will explain the pivotal role Verisense plays within the dAGI technology stack and the three major technical contributions it offers to address key industry challenges. By the end of this lesson, we expect each participant to have developed a comprehensive understanding of the Verisense project, its creation context, the core problems it addresses, and the new possibilities it introduces. We are witnessing significant technological paradigm shifts. Artificial intelligence (AI) is transitioning from relying on large, centralized models to a collaborative network of numerous small, autonomous, and distributed agents. This shift has introduced two closely related concepts: decentralized artificial intelligence (dAGI) and multi-agent systems (MAS). Decentralized artificial intelligence (dAGI) represents more than just a fusion of AI and blockchain. It signifies a completely new way to organize and operate AI. Its core idea is to decentralize all components of artificial intelligence, ranging from the foundational GPU computing resources to the data and models, up to the agent applications. It involves integrating blockchain with advanced AI technologies, like large language models, LLMs, to create an open and trustless intelligent ecosystem, distinguishable from traditional centralized AI. This shift is crucial as it offers a path to avoid domination by a single, centralized super AI, ensuring AI development remains secure, fair, and inclusive through distributed governance and control. Multi-agent systems, MAS, are the practical application of the dAGI philosophy. These systems comprise multiple intelligent agents that can independently perceive their surroundings, make decisions, and collaborate to solve complex problems beyond the capability of a single agent. These agents might include AI-driven software services, IoT devices, autonomous vehicles, or any digital entity capable of autonomous behavior. Within AMAS, each agent operates with its own goals and knowledge, and their interactions and collaboration form the heart of the system. For instance, in managing a complex supply chain, different agents might handle inventory monitoring, logistics scheduling, and market demand forecasting, thereby enhancing the efficiency of the entire process through coordinated efforts. The emergence of dAGI and MAS demands a robust infrastructure. As thousands of autonomous agents need to exchange value, share data, and coordinate complex tasks, they require a decentralized platform capable of supporting dynamic, adaptive, and frequent interactions. This need forms the essence of Verisense's purpose. While traditional blockchains facilitated low-frequency, human-initiated transactions, the dAGI era features machines, agents operating autonomously 24/7, interacting with the physical and digital worlds. Thus, the dAGI trend spearheads the development of Verisense. It addresses a critical infrastructure need in the dAGI era, establishing a reliable operational foundation for what is termed the agent economy. To grasp the innovative value of Verisense, we need to first delve into a fundamental challenge facing current blockchain technology, known as the passive dilemma. Traditional blockchains, such as Bitcoin and Ethereum, function as passive, deterministic state machines. This design aims to ensure the network's security and consistency. As long as all nodes process transactions in the same sequence, they will reach an identical state. While this aspect is beneficial for financial transactions, it also imposes several limitations on smart contracts. Trigger dependency. Smart contracts cannot initiate actions independently. They require an externally owned account, EOA, to trigger them by sending a transaction. Without this external stimulus, they remain inactive, like engines waiting for a command to start. Limited data access, confined within a sandbox. Smart contracts cannot proactively access external information. They cannot directly interact with websites, databases, or off-chain data sources. Instead, they rely on third-party services known as oracles to provide necessary data, rendering them blind to external information and limiting their interaction with the real world. Lack of time awareness. Smart contracts do not possess a built-in, reliable time-driven mechanism. They cannot autonomously schedule tasks for future execution based on a specific time or block height. Instead, they depend on external automation services to send transactions at the right time, introducing centralized dependencies and additional costs and complexity. Think of a traditional smart contract as a skilled legal expert trapped in a sealed room. He can execute contract terms flawlessly, but only when someone passes the transaction into the room. He cannot step outside to gather evidence or set future tasks himself. The Verisense white paper highlights traditional blockchain architectures are passive by design, a limitation that is increasingly inadequate in the era of decentralized AGI, dAGI, where dynamic, adaptive, and interactive agentic systems are becoming critical. This passive dilemma hinders the ability to build truly autonomous on-chain agents that can proactively respond to real-world changes, forcing continued reliance on centralized, trusted external components. This reliance conflicts with the core principles of decentralization and trustlessness in blockchain technology, forming a significant bottleneck in the development of dAGI. In the second part, we explore Verisense's core innovation, known as the active blockchain. To address the passive nature of traditional blockchains and build an infrastructure suitable for the dAGI era, Verisense has developed and implemented a groundbreaking blockchain paradigm. This innovation is not merely a functional enhancement. It represents a profound architectural shift that fundamentally redefines how on-chain programs interact with the external world. An active blockchain is defined as a system in which its on-chain programs, such as smart contracts, can independently access external data and schedule future tasks, all while incorporating these activities into the blockchain's consensus. This concept includes two main active features. First, there's proactive external data input-output. This means the on-chain program itself can initiate a network request. For instance, an agent program, like a nucleus on Verisense, can directly make an HTTP request to retrieve the most recent prices from a financial API or extract headlines from a news site. This process happens within the blockchain, with the authenticity and integrity of its results ensured by the network's consensus. Second, there's proactive task scheduling. This allows the on-chain program to autonomously handle the timing aspect of its operations. It can set an internal timer to automatically execute predefined logic at a certain blockchain height or time. For example, a decentralized social application could automatically settle users' earnings daily without needing any external service to intervene. The Verisense white paper details a significant paradigm shift by introducing an extended state machine model. Traditionally, A blockchain is represented as M equals X sigma T F, with sigma as the state space, T as the set of transactions, and F as the state transition function. The concept of an active blockchain is an extended model given as M equals X sigma E T F. Here, the event set E is significantly expanded to include not only transactions initiated by external accounts, but also internal events generated by on-chain programs such as asynchronous external call events and timer trigger events. At any block height, its state transition can be described by ST+1 equals FST in capital XI. The essence of this extended model is that it incorporates active behaviors such as API calls and task scheduling, which were previously external to the blockchain, directly into the blockchain's state transition function. Through rigorous cryptographic proof methods like threshold signatures or zero-knowledge proofs, Verisense ensures that even with these incorporated interactions, every state transition remains deterministic, verifiable, and agreed upon by all nodes in the network. This approach fundamentally addresses the tension between proactivity and blockchain determinism. The transformation introduced by the active blockchain paradigm is fundamental. To better grasp its innovations, it's helpful to compare it with traditional passive blockchains across various aspects. The core differences between active and passive blockchains lie in several key areas. Firstly, the execution model. Passive blockchains operate reactively, triggered entirely by external transactions and waiting to execute instructions. In contrast, active blockchains are proactive, capable of self-triggering actions and initiating external requests while scheduling future tasks. Next is the interaction pattern. Passive blockchains rely on trusted external oracles for data feeds, effectively outsourcing interaction capabilities. Active blockchains, meanwhile, have built-in capabilities for proactive external calls, such as HTTP requests, making interaction a core function of the blockchain itself. Regarding the trust model, passive blockchains trust a deterministic state machine and have separate, often centralized, reliance on oracles. Active blockchains, however, rely on a distributed network of validators to verify external interactions, utilizing cryptographic proofs like zkTLS for trustless data input-output. In terms of data access, passive blockchains receive data pushed from the off-chain world, whereas active blockchains allow on-chain programs to actively pull necessary data from external sources. When it comes to use cases, passive blockchains focus largely on tokenization, DeFi involving purely on-chain data, and digital ownership such as NFTs. Active blockchains, however, facilitate applications like decentralized artificial general intelligence, dAGI, on-chain autonomous agents, real-world data-driven automation, IoT, and cybernetic contracts. Finally, their core challenges differ. Passive blockchains face issues with scalability, gas fees, and transactions per second. Active blockchains need to ensure the verifiability, consistency, and attack resistance of external interactions without compromising consensus security. Through this comparison, it's evident that their design philosophies are fundamentally different. Passive blockchains create a secure, closed digital environment, prioritizing simplicity and determinism but remaining isolated from the real world. They outsource the complexity of external interactions to oracles, which reintroduce centralized trust elements. Active blockchains take on the external world's complexity directly and design mechanisms to integrate this interaction within the realm of consensus. By using cryptographic techniques to manage external uncertainties, every proactive interaction becomes verifiable, auditable, and trustworthy. This transition moves the trust model from relying on oracles to depending on cryptography and decentralized consensus, marking a significant leap forward. This paradigm shift results in diverse application scenarios, where passive blockchains excel at handling scenarios that are logically closed and self-sufficient in data, like token issuance and trading. Active blockchains enable dynamic, autonomous interaction with the real world, which is crucial for dAGI and autonomous agents. Verisense's active blockchain paradigm brings forward significant advancements in the dAGI stack, establishing unique value propositions. Here's how Verisense enhances the dAGI ecosystem. Verisense revolutionizes on-chain AI agent operations by providing a platform for hosting, executing, and discovering agents. Traditionally, AI agents are hosted on centralized cloud servers, making them susceptible to external control and lacking transparency. Verisense transforms this scenario by executing AI agents as cybernetic contracts directly on the blockchain. These agents are equipped with cryptographic identities and immutable interaction histories, allowing their actions to be verifiable and auditable. This enables agents to function as autonomous digital entities governed by code, fostering a trustworthy and controllable agent society, in addition to offering a secure environment for individual agents. Verisense serves as a universal collaboration platform, enabling diverse agents to interact and leverage each other's capabilities. Unlike rigid workflows, Verisense's dynamic sense space allows agents to engage as peers, creating a collaborative environment where AI applications can utilize multiple agents' tools. This interactive space functions as an agent marketplace where developers can craft sophisticated applications by combining various agents' specialized skills. These propositions together form Verisense's vision of becoming an integral part of the dAGI civilization, akin to an operating system for AI agents. The agent hosting and execution aspect acts as the kernel, providing a secure environment and managing resources, while the sense space facilitates multi-agent collaboration, comparable to inter-process communication mechanisms. By positioning itself as a decentralized operating system for AI agents, Verisense lays the groundwork for a foundational platform in the dAGI era, transcending the creation of a mere public blockchain. Verisense, building on the innovation of the active blockchain, offers a comprehensive technical architecture and systematic solution designed to address the challenges of the dAGI era. It embodies this approach through 3 core technical contributions and provides answers to 4 fundamental problems facing the industry. Verisense's technical innovations can be encapsulated in 3 key contributions that form the technological foundation of the Verisense network. Firstly, Verisense introduces a unique blockchain architecture designed for seamless collaboration between autonomous agents. This architecture inherently allows for dynamic, peer-to-peer agent communication and on-chain decision-making, evolving from mere transaction records to a dynamic platform ideal for agent communities. The layered architecture, monitoring subnets, and nucleus execution environment, which will be detailed in future discussions, exemplify this innovative approach. Secondly, Verisense has developed novel consensus mechanisms focused on both agent hosting and security. These mechanisms are crafted to ensure that on-chain agent operations are secure and autonomous, maintaining the integrity of interactions. They confirm that multi-agent collaborations are executed flawlessly and that agent states remain tamper-proof and consistent throughout the network. A prime example is the monitoring lightweight consensus protocol, which enables efficient and low-cost validation as a service, VAS. Lastly, Verisense presents SenseSpace, a universal environment that enhances the creation of decentralized intelligent applications. SenseSpace replaces rigid workflows with a platform where agents can be published, discovered, and interact directly. Developers can craft agents providing specific tools or capabilities, allowing other agents or applications to utilize these tools as needed. This modular, peer-to-peer model facilitates the development of scalable and adaptive multi-agent applications, reducing development barriers and enhancing composability. Together, these 3 contributions define Verisense's technical strategy: a powerful architecture as the framework, an innovative consensus system as the security assurance, and a versatile interaction platform as the engine for application development. They collectively support Verisense's overarching vision to serve as the infrastructure in the era of decentralized artificial general intelligence, dAGI. To create a blockchain platform that can support dAGI, it is essential to address 4 primary challenges that stem from its core attributes. At the heart of Verisense's design philosophy is the systematic resolution of these challenges. Firstly, there is the challenge of coordination among autonomous agents. In a decentralized network, each agent acts independently, driven by its own goals and the information it possesses. The question is how to ensure that these diverse and self-interested agents can collaborate effectively without causing conflict or system instability. Verisense tackles this through SenseSpace and its foundational decentralized communication protocols, such as DMCP and dA2A. This creates a unified coordination environment that enables dynamic interactions. Instead of following set workflows, agents can discover one another's capabilities and negotiate their interactions in real time, facilitating complex and adaptive collaboration to achieve tasks. Secondly, ensuring security and privacy is crucial. Agents need to exchange data and make decisions in environments that might not be trusted. The concern is how to protect data from theft or tampering during interactions, and how to handle sensitive information like personal data or trade secrets. Verisense utilizes multi-layered cryptographic strategies. Its innovative consensus mechanisms, such as monitoring, incorporate technologies like threshold signatures to secure collective decisions. For external data interactions, protocols like Proof of Data I/O, based on zk-TLS, verify data authenticity and integrity. Moreover, Verisense integrates advanced technologies like fully homomorphic encryption, FHE, to allow computations directly on encrypted data. Through the Proof of Semantic protocol, the most semantically relevant results can be identified without exposing any party's information. The third challenge involves creating robust incentive mechanisms. A sustainable agent ecosystem needs incentive structures that encourage honest participation and collaboration. Poorly designed incentives may spark selfish behavior, free riding, or inadequate resource contributions. Verisense addresses this with its unique combination of architectural and economic models. Its reverse gas model, where application publishers shoulder the computational costs instead of end users, reduces user barriers and incentivizes widespread application use. Additionally, by integrating with the restaking ecosystem, where validators earn rewards for honest conduct and risk slashing for malicious acts, Verisense assures the network's security and dependability. Finally, there is the need for modular and extensible frameworks. The scenarios for dAGI applications are diverse, as are the functions and operating environments of agents. The underlying framework must be modular and adaptable to diverse requirements without compromising interoperability. Verisense's architecture is inherently modular. The Nucleus execution environment allows developers to deploy independent, customized, and sandboxed mini blockchains, monitoring subnets. Tailored to specific applications, developers can adjust the number of validation nodes based on application needs, balancing security, cost, and performance. This app chain design offers significant flexibility, while SenseSpace ensures that agents in varied environments can still interact and collaborate. These challenges are interlinked. A modular framework without security is ineffective, and coordination without strong incentives is unsustainable. Verisense's true strength lies in its ability to provide an integrated, comprehensive solution by addressing these challenges collectively. When developing a complex dAGI application, such as a BTC quantitative trading bot, Verisense offers complete end-to-end support, including secure runtime through Nucleus, modular interaction framework via SenseSpace, agent coordination using dA2A, security and privacy with Proof of Data I/O and FHE, and incentivization through restaking and tokenized economic models. This comprehensive design philosophy establishes Verisense as a pivotal infrastructure in the dAGI era. In this lesson, we have explored the emergence of the Verisense network, its core innovations, and its significant value. Let's recap the key points we covered today. We first identified that with the development of decentralized artificial intelligence, dAGI, and multi-agent systems, MAS, the limitations of traditional passive blockchains have become evident. These blockchains fall short in meeting the essential needs of future autonomous agents, which require proactive interaction, data acquisition, and task scheduling. Next, we discussed the definition of Verisense's fundamental paradigm innovation, the active blockchain. This groundbreaking architecture integrates external interactions and time scheduling into the consensus process, granting on-chain programs true autonomous agency for the first time. This shift transforms them from passive executors of instructions to active participants in the world. Lastly, we highlighted Verisense's value proposition. It serves not only as a platform for the secure hosting and execution of agents, but also seeks to enable universal multi-agent collaboration through its interaction environment, SenseSpace. With its three major technical contributions, Verisense offers a complete, integrated, and systematic solution to the four fundamental challenges in the dAGI field. Verisense heralds a new era of cybernetic contracts, creating a cybernetic society comprised of verifiable, auditable, and autonomous on-chain agents. In our next lecture, we will explore the technical core of Verisense, examining its innovative monitoring consensus protocol and the nucleus environment for agents in detail.